Hello everybody, today I'll be talking about my process of validating a diagenic model which considers the organic carbon flux from aquaculture cages to the sediment, how it reacts in the sediment, and the outputs it produces, which can be used to help determine health of the sediment in the future. My model is a smaller component of a much larger model which considers hydrodynamic activity and then uses that to produce waste deposition output, which then comes into my model, and then I run through diagenesis. So you take your hydrodynamics and your cage setup for aquaculture, that sends the information to organics, which produces the organic matter flux. I take that flux, run it through my model, and get sulfides and remaining organic carbon output. As a means of validating my model, because you have to ground truth your model for anyone to consider it viable, I've been taking measurements in the Shelburne in southern Nova Scotia at 3 different sites, 2 inner harbor, high porosity, high organic matter sites, and 1 near the open ocean with very high energy, low porosity site for means of validation. Now, I am not the only one that's been doing measurements at each site. The provincial government and sometimes the federal government mandates that 4 major variables be measured annually at farm sites. Be it organic matter or LOI, dissolved sulfides, porosity, and redox potential. Now, each of these are compared to reference sites in the surrounding area. As I mentioned before, these green dots show the measurements at the reference sites, and the bars are the means at the active farms. And if the accumulation is too great of sulfides, this can impact the health of the invertebrate. And then we have different zonations based on how much sulfide is accumulated. Down here, these represent certain concentrations. And if some of these concentrations are reached, then we need to change the management strategy, amount of fish, cage layouts, feeding, all that kind of stuff. That will need to be changed to accommodate or to try and mitigate the impacts of the dissolved sulfide. Now, I won't go into the exact relationship between the 4 major variables that are measured as a proxy for sediment health. Just consider that the dissolved sulfides are used as the most direct, and then redox, organic matter, and porosity are kind of used as checks when comparing the lease versus the reference sites. Now, these are density graphs, so these are frequency of measurements of these specific variables. And this is the reference site or no fish present and fish present sites. And the reason I have this up is because I wanted to show the differences between the 2 sites. And the majority of fish farmed in Shelburne are salmon, and you stock your salmon in the pens in springtime, and then the grow-up period is about 1.5 years. Now, the provincial government does their measurements, it occurs in July and August. Now, the thing is, we don't know at what point, when the measurements were taken, at what point in the grow-up process this was occurring. So it would be a couple months after stocking, or 1.5 years after, or just a bit over 1 year after stocking. So if you're going to take your measurements very quickly or very soon after stocking occurs, you're going to have results at the least that are more similar to the reference site in comparison to 1 year later, where you're more likely to have more organic matter, higher sulfides, and lower redox potential. So these curves over here, you could probably fit them within these curves at the least, showing that the measurements taken at the least oftentimes were similar to the reference site, and then at other times, we got maybe some higher porosity or lower porosity, and higher organic matter distributions, significantly higher. If you look at the differences in x-axis here, significantly higher in sulfides, and push more to the left under redox. Now, to see the differences in years between active and reference sites, what I've put together here is this little comparison of the measurements taken in each of those groups and comparing the distributions if they're significantly different or not. And a secondary layer added onto this is, as I mentioned before, I managed to get information on whether fish were present or not. So we've got the years here, the 4 major variables considered for benthic health, and then 3 different lease sites. Gray squares represent no measurements taken. Blue and yellow are when fish were present, and then green and red are when fish were absent. Now blue is no significant difference between lease and reference sites, and green is no significant difference between lease and reference sites. Just the difference is whether fish are present or not. Fish present, fish not present. Now, what's interesting about this, and this talks about some natural variability in the system or some homogenizing event that makes everything similar, is fish were removed from Sandy in 2011, as we can see here, and they continued to monitor for 4 years afterwards. And now you can see here that it took a long time before they even stopped measuring until the reference site was similar to the lease again. However, in 2014, you can see that redox returned to similar levels as the reference site and between the reference and lease sites. So this suggests there was some large homogenizing event at a large scale, which pushed the two back together. And there was no fish reintroduced back here or anything like that. And then it moved back down to being significantly different. So some major event, other forcing other than a farm presence occurred. And you can see kind of like little blips back and forth here, inconsistencies that would suggest something like that if nothing changed at the farm. Moving on to outside of the measurements that I took and or historically take, we need to consider the variability of certain parameters and state variables within the model itself. Now, when we're looking at the environmental monitoring program measurements for organic matter, it's just a total organic matter, a percent organic matter of the sediment. However, for my model, I only need to consider the organic carbon content in that organic matter, which is a percent by weight of the total organic matter. And that could vary based on the source of the organic carbon. We look at the feed, carbon content of feed, fish feed around 50%, and then only half of that around for the feces as well. And so we can't just have one basic organic carbon flex. We need to know like at what ratio there is present as well of that organic matter coming in. So not only is the organic carbon content in organic matter variable, but the decay rate, the breakdown of organic matter can be quite variable as well. And you can have the same metabolic pathway, be it through oxygen, sulfate, or nitrogen, but the rate of breakdown can still vary quite wildly. Very common in these diagenesis models is to have 3 pools of organic matter, each of them decaying at a different rate. Refractory here being much slower, semi-labile somewhere in the middle, and labile being much faster. I wrote this as farm origin because studies have shown that farm origin organic matter can break down quite rapidly. And a rapid breakdown initially seems good, we're getting rid of this organic matter. However, a rapid breakdown is partnered with a rapid accumulation of dissolved sulfides, which, as I mentioned, can be toxic to benthic invertebrate. So we have these different speeds of breakdown, and this can create different peaks in the amount of dissolved sulfide in the sediment. So we could have a peak near the surface, a peak in the middle, and a peak at the bottom, depending on if there's sulfate available to break it down and at what depth the organic matter has gone down. So we need to kind of find a balance between different origins of organic matter and different decay. Then we have biological transport, a major component. When I did sensitivity analysis for my diagenetic model, the impacts on transport obviously were the most sensitive as opposed to chemical reaction rates. So biological transport is going to happen somewhere between the sediment water interface and a depth, and looking at a large database of DB being bioturbation or biologically mediated transport could be from 0 to 150 centimeters deep. Generally, it's probably going to be between 0 to 15 centimeters deep. Shelburne, it was measured before, it happened to be around 7. And then the rate of exchange of solutes and solids can also vary quite wildly. Then you also have the various species that interact with each other. Mass, body size, biodiversity in the sediment, rarity of the species, and stress sensitivity all impact species differently, which can heavily impact the extinction rate in a specific environment, and the specific environment in a cell or the surrounding cells and how they interact, and that can change from one to the next. So how do I address all this variability, all these factors outside of my control, and how do I validate my model with only having, annual monitoring of the upper layer of sediment. Well, my approach was to take the initial conditions of the measurement, say at the mean of a reference site, of the reference sites surrounding the lease, use that as a starting point, and then take the good observations found within the environmental monitoring program data and subtract the two, and from that get a rate. And I've assumed here, at least, I've assumed that this is the later, the end of the grow out period for the salmon. So for this, it's 15 months. And then, so on these axes, I have the accumulation rate per month. So how much the organic matter percent has increased and how much the dissolved sulfide concentration has increased each month. So we've got some high sulfide accumulation values here, and while that's happening, the organic matter is going up rather slowly, whereas the inverse here, we have rapid organic matter accumulation rate and low sulfide accumulation over this period. Now, why would that happen? Now, this could very well be related to the mixture of the different ratios of the mineralization rates of the organic carbon that's coming down to the sediment. So we've got our fast, medium, and slow decay here, and changing and making a ratio of the flux of carbon that's coming down, organic matter that's coming down, we can change, or you see changes in accumulation rates. You know, very fast decay, a lot of sulfide. Slow decay, a lot of organic matter in comparison. So these three curves here, they capture the rates quite well. And each of these little crosses here indicates 1 gram of carbon per meter squared per year change in flux. So this would be 1, 2, 3, 4, 5, increasing in flux as we go up the graph. And that's it. There's not a ton of time, so if anybody has any questions, please feel free to ask.